Okay, good afternoon, everybody. Welcome to the last session. And today our first speaker is Masafumi Udagawa, and he's going to tell us about dynamics of fractional excitations in Kitaev spin liquid.
Okay, so first of all, I'd like to thank the organizers to give me an opportunity to talk here. My name is Masafumi Udagawa from Gakushu University, and today I'll talk about my recent work on dynamics of fractional excitations in Kitaev spin liquid. This work is already on the archive, and I hope it will be published soon. Okay, so the outline of my talk is here. Okay, the main issue of this talk is Kitaev spin liquid. Already several speakers have mentioned this model, but firstly, I will introduce this model and some background materials, especially related to my talk. Okay, and in this talk, I'll address the dynamics of Kitaev spin liquid. Recently, I formulated the exact analytical solution of dynamical correlation function of Kitaev's model. By incorporating this solution into classical Monte Carlo scheme, we can fully explore the dynamical properties of this model. So in the second part, I'll give an introduction to this scheme. Okay, in the third part, I will address the dynamical response of Kitaev spin liquid, especially in the presence of impurity. In particular, I'll focus on the zero-energy resonance appearing in the neighborhood of site vacancy, which turns out to reflect an essential property of fractional excitation called boson. Okay, so let's start with the introduction. So the main topic of my talk is Kitaev's model. Recently, many variants of this model has been considered and intensively studied, as Okubo-san discussed in the previous talk. However, in this talk, I'll consider the most primitive version of this model. The model consists of spin 1/2 defined on a honeycomb lattice, and the spins are interacting with each other through the Ising type interaction. Along the red bonds, spins want to align in X direction, and along the green and blue bonds, they want to be parallel to Y and Z directions, respectively. Okay, so the one remarkable property of this model is, of course, it is exactly solvable. The first and the most important step to solve this model is to express each spin by Majorana operators. Namely, we introduce 4 Majorana operators per site and express each spin component as a product of 2 of them. Then you can rewrite the Hamiltonian as a quadratic C Majoranas coupled with conserved static gauge fields, which are defined as the products of neighboring P Majoranas. Then, since the Hamiltonian is now quadratic, you can easily diagonalize it. However, this is not the whole story. So far, we have expressed each spin by 4 species of Majoranas. So the dimension of Hilbert space is doubly enlarged per site. This problem appears as gauge redundancy. So suppose, again, so the spin is a product of 2 Majoranas. This means if you multiply -1 by 4 Majoranas at one particular site, it preserves the spin and it won't change anything. However, the gauge field changes sign. So this means several sets of gauge fields configurations correspond to one identical physical state. So instead of gauge fields, we focus on its gauge invariant combinations, namely a product of 6 gauge fields around a hexagon. This quantity takes ±1, and we call it Z2 flux. So instead of gauge fields, by classifying all the states in terms of these Z2 fluxes, you can eliminate most of the unphysical states. And the final point is fermion parity. Again, the spin operator is a product of 2 Majoranas. So this means 2 Majoranas always come together. You cannot make a single Majorana excitation. So this gives a constraint on fermion parity. So summarizing so far, the procedure to obtain exact solution is divided into 4 steps. Firstly, fix the Z2 fluxes. Then secondly, fix the gauge and determine all the values of gauge fields. And thirdly, diagonalize the quadratic Hamiltonian. And finally, select the states with correct fermion parity. After these 4 steps, you can finally obtain the whole eigenspectrum of Kitaev's model exactly. Okay, so the procedure to obtain exact solution is a bit involved, but the structure of obtained ground state is rather simple. If you consider the anisotropic coupling constant, then the ground state phase diagram looks like this. So it consists of 2 phases, gapless gap through A phase and gapless B phase. Both phases have short-range spin correlations, suggesting that these states are rarely quantum spin liquid states. Okay, in the previous slide, I talked about the classification of states in terms of Z2 fluxes. And in terms of this classification, the ground state belongs to an extremely simple sector where all the Z2 fluxes take +1. So in other words, a hexagon carrying Z2 flux -1 can be considered as a sort of excitation. And we call it bison. So in this system, we have 2 species of excitations. One is concerned with C Majorana, and it excites fermionic excitations. And the other is bison. So bison is created by B Majoranas, and it is always pair created. And so fermionic excitation can be gapful or gapless, depending on which phase the system belongs to. But a bison is always gapped. So bison works as a pi vortex for the fermions. And so it gives a pi phase shift for fermions going around the bison. And through this scattering process, it pushes up the kinetic energy of fermion. And this energy increase is interpreted as the bison gap. Okay, so this is the basic structure of Kitaev's model. On the experimental side, we have several candidate materials. One is a very recent one. It's a hydrogen intercarnated lithium iridate. So in this compound, iridium ions support a 1/2 spin and form a honeycomb lattice. And no magnetic ordering is found down to very low temperature, like 1 Kelvin. And another compound is ruthenium trichloride. In this case, in this compound, you have magnetic order below around 10 Kelvin. Nevertheless, this compound is considered as a promising candidate for Kitaev spin liquid because the low temperature zigzag magnetic pattern is found in the vicinity of spin liquid phase in the numerical analysis of Kitaev-Heisenberg model. Okay, then for this ruthenium trichloride, several observations have been made for its fractional excitations. Inelastic neutron scattering studies have revealed continuous spectra. So it means single spin excitation is decomposed into several fractional excitations. This is one interpretation. However, this continuum does not seem to still convince everyone of the existence of fractionalized excitations in this system. A major objection is, on one hand, continuum is a natural consequence of fractionalization, but on the other hand, continuum does not necessarily require fractionalization. For example, a multi-magnum process can be considered as another possible origin, and such possibility was already pointed out. So considering this ambiguity, it is desirable to have a clearer diagnosis into the existence of fractional excitations. And regarding the fermionic excitation, even more strikingly, there is a report on the half-integer plateau of thermal Hall conductivity. So it implies a realization of Z2 chiral spin liquid phase. And according to the original prediction by Kitaev himself, so this effect results from the chiral Majorana edge modes. So this is an interesting contribution from the Majorana mode, I mean the fermionic excitation. But in contrast, so far, there is no practical reports on the existence of bosons. So again, it is desirable if we have a way to identify the boson and clarify its character, and hopefully trap and control it in realistic experimental setting. Okay, so for this purpose, in this talk, I'd like to consider the effect of impurity. Impurity usually conceals rather than clarifies the true nature of the system, but in the context of quantum spin liquid or the system of topological nature, impurity or sample edge historically serves as an essential tool to clarify its ground state or excitation characters. So following the classic success, I'd like to consider the impurity effect also in the context of Kitaev's spin liquid and try to make a better understanding on the nature of its fractional excitations. Okay, so let's move to model and method. So in this talk, I'd like to focus on the isotropic ferromagnetic Kitaev's model. In order to study its finite temperature properties, we use classical Monte Carlo method by sampling conserved Z2 fluxes. In each realization of Z2 flux configurations, we diagonalize the Hamiltonian and determine its statistical weight from its fermionic partition function, whose calculation gives a computational bottleneck in this analysis. And with this scheme, we calculate the correlation function defined like this. So the real part of this function can be associated with the spin-lattice relaxation rate, 1 over T1. And the imaginary part can be connected to the magnetic susceptibility. So both quantities can be accessible through the, for example, NMR experiment. And one important property of Kitaev's model is that the spin correlation is extremely short-ranged. So it results from the conserved nature of Z2 fluxes. Suppose you make a spin excitation, then inevitably you have to excite boson and fermion at the same time. But because the Z2 flux is conserved, the excited boson cannot propagate anywhere. So eventually it has to vanish almost in a place where it is created. So this is why the spin correlation at most extends to nearest neighbor in this model. Okay, then the full expression of spin correlation function is like this. So this is the first result of my work. So this work still contains the summation over the Z2 fluxes. So in order to evaluate this quantity, we need some numerics. Nevertheless, this expression is extremely useful since it allows us to directly access the correlation function in real-time representation. So without analytical continuation, you can obtain the spectrum, correlation spectrum, in real frequency scheme. So I obtained this expression by using Majorana expression. The Hamiltonian is already quadratic, but still the analysis is not that straightforward. The Hamiltonians entering these two time evolution operators differ because of the excited bosons. So it is not that easy to evaluate this correlation function. You encounter this type of correlation function in a class of problems called X-ray edge problem. And usually, you solve so-called Nogel-Dominicis equation to obtain this type of correlation function. However, if fluctuating fields exist in the system, it is practically impossible to solve this equation to obtain this correlation function. So our exact solution gives a new approach to a generalized X-ray H problem. So it's potentially applicable to a much wider range of problems beyond Kitaev's physics. Okay, so equipped with this knowledge, let's move to results. So firstly, I'll show you the on-site spin correlation in real-time frame. So at this relatively high temperature, the correlation function immediately decays with small oscillations. However, if you go to lower temperatures, the oscillation sustains for a longer time. And in a temperature range of our interest, the oscillation typically continues like to 200. So in our calculation, we set this 200 as an upper limit, upper cutoff of our analysis. So with this upper limit, we numerically Fourier transform this time dependence and obtain the real frequency dependence of correlation functions. So this is the real part, and this is the imaginary part. And their zero energy components are associated with 1/T1 and local magnetic susceptibility, respectively. So we can evaluate these type of correlation functions as a function of real frequency. Usually, it is not that easy if you use numerical analytical continuation. Okay, then let's see how this correlation function develops as changing temperatures. So firstly, this is the plot of specific heat. We have two energy scales in our system. So reflecting these two energy scales, the specific heat has double peak structures. The higher temperature peak corresponds to the energy scale of C-Majorana, or fermionic excitation. And the low temperature peak means the entropy release by bosons. So corresponding to this specific heat, the on-site spin correlation spectrum develops like this. So from the high temperature side, beyond the high energy fermionic peak, then the spectrum has rather broad feature. However, as you decrease temperature beyond the low energy boson peak, some continuum is formed at higher energy. And on top of that, there is a quasi-resonant low energy peak is developed. However, this low energy peak is not located right at zero energy, but it's at finite energy. So in order to make a spin excitation, you have to create a pair of bosons, and the boson is gapped. So this finite energy excitation corresponds to the excitation of boson gap, pair boson gap. Okay, so if you translate this spectrum into observables, you can obtain this plot. This is the temperature dependence of 1/T1. So from the high temperature side, it shows some increasing behavior as decreasing temperature. Then it shows a peak at some temperature, then turns to decrease and shows some exponential decay. This behavior can be interpreted from the temperature evolution of this spectrum. So the zero energy value of this spectrum can be associated with 1/T1. So starting from the high temperature side, firstly, the spectrum is very broad, but as decreasing temperature, it grows some sharp low energy peak. And accompanying this, 1 over T1 shows some increase. However, this low energy peak is not located right at 0, but at finite energy of Wison gap. So eventually, it shows a peak and turns to decrease with exponential decay. So you can understand this behavior. And for the magnetic susceptibility, we have a plot like this. So similarly, this magnetic susceptibility shows a peak around here. Then it goes to the some finite value at low temperatures. Okay, so far we have all the results without impurity, but let's introduce impurity here and look at how these magnetic behaviors will be changed. Okay, so we introduce single impurity, and specifically, we consider the case of site dilution. We remove one spin completely. Even in the presence of impurity, the site vacancy, the Kitaev's model is still exactly solvable, and the solution inherits many important properties, such as the extremely short-range correlation. So we consider this problem in a system size of 200 sites. So 200 sites is already very large enough. And according to the calculation in the absence of impurity, this system size is well within the convergent system size. Okay, so let's look at the results with site vacancy. Firstly, this is the Vark spectrum without vacancy. So this is the same spectrum as I showed you in the previous slide, but plotted in the different energy scale. Then let's introduce site vacancy at site 0. Then in the presence of site vacancy, the correlation function depends not only on the distance from the vacancy, but also which component of spin you are looking at, X, Y, or Z. So firstly, the SY correlation, 6 sites away from the vacancy, almost overlaps with the Vark spectrum. So with this distance, the spin dynamics almost recovers the Vark behavior. However, as you approach the vacancy site, the spectrum deviates from the Vark value, and typically, the low energy peak grows very sharply. Okay, so let's look at the behavior in the language of observables. For this purpose, let's choose 2 directions of high symmetry starting from the vacancy site and plot the local magnetic susceptibility along these directions. Firstly, at higher temperatures, higher than the high energy fermionic peak of specific heat, then the local magnetic susceptibility is almost flat, and it has no substantial spatial dependence. And its tendency continues to somewhat lower temperatures. And at lowest temperature, beyond the low energy Wison peak, it finally shows some disturbance, and it increases around some vacancy site. So if you look at the temperature dependence, selecting several sites near the vacancy, you can obtain a plot like this. So from this plot, you can find the local magnetic susceptibility almost overlaps, almost has no difference between the sites for a very wide temperature range. And only in the temperature scale of Wison peak, it starts to bifurcate. In the previous study of impurity effect, there was a prediction that the local magnetic susceptibility diverges toward t equals 0 in a logarithmic way. Perhaps this uprising behavior connects to logarithmic behavior at lower temperature, but in our analysis, considering the Wison fluctuations, at least this logarithmic temperature regime is confined to very low temperature regions. Okay, so this is local magnetic susceptibility, and let's see the local 1 over T1 next. Similarly, let's plot the spatial dependence of local 1 over T1 at higher temperature compared with the high energy ferromionic peak. Then, in contrast to local magnetic susceptibility, you already have some slight disturbance around the site vacancy. And as you lower the temperature, this spatial modulation becomes conspicuous. It shows drastic oscillatory behavior reminiscent of Friedel oscillation. And if you decrease the temperature further, the 1 over T1 itself is suppressed, but the oscillatory behavior sustains. So in contrast to the magnetic susceptibility, this dynamical 1 over T1 shows the large spatial dependence. However, despite this large spatial dependence, the qualitative temperature dependence of 1 over T1 is not that different. So almost all the sites show the single peak behavior with exponential decay at lower temperatures. However, there is one curve. It shows a totally different behavior. So the local 1 over T1 just next to the vacancy shows a totally different temperature dependence. In contrast to the single peak behavior at different sites, it shows almost a featureless flatness for a very wide temperature range. And in the temperature scale of Bison peak, it finally shows a slight upturn. So how can we account for this anomalous behavior? To understand this, let's look at the full spectrum of on-site correlation next to the site vacancy. Then you can find a very sharp zero energy peak around here from the relatively high temperature. Since 1 over T1 is proportional to this peak height, obviously this anomalous zero energy resonance is responsible for that upturning temperature dependence of 1 over T1. Okay, however, such a sharp resonance is elusive in a system with fractionalization. So in our system, the spin is a complex object of B Majorana and C Majorana. B Majorana excites bosons, and C Majorana excites ferromionic excitations. So in order to have a sharp zero energy resonance, you must have a simultaneous zero mode of ferromionic excitation and boson at the intermediate state. So how can it be possible? It is the question. So in order to understand the origin of this simultaneous zero mode, let's look at how boson affects fermions in the vicinity of vacancy. So boson is a pi vortex for fermions. So it gives a pi phase shift to fermions going around the boson, okay? So that scattering process pushes up the kinetic energy of fermions, and this is interpreted as a boson energy. However, in the vicinity of site vacancy, if you make a spin excitation, then you create a pair of bosons in the vacancy cage. And the fermionic excitations cannot enter this vacancy cage. So it can only go around this cage. So it feels the phase shift from two bosons at the same time. So the situation is similar to the fermions propagating around the Dirac solenoid. So because fermions feel the phase shift from two bosons at the same time, they feel always the phase shift of 2 pi, so they feel nothing. So that's why the kinetic energy of fermions stays the same, and accordingly, boson gap locally closes. So this is the origin of the formation of boson zero mode. And on top of boson zero mode, you have a fermionic zero mode. So because of the site vacancy, fermionic part also is affected. So this green line shows the fermionic density of states, and it shows a sharp zero energy peak in the vicinity of vacancy. And this zero energy peak is absent in the bulk spectrum. In fact, this fermionic zero mode can be understood as an analogy of vacancy state known for graphene. In graphene, graphene has the same bundle structure as Kitaev fermions. And in the context of graphene, if you introduce site vacancy, it is known that a quasi-localized state is formed around this vacancy. And this picture of quasi-localization well accounts for this temperature dependence of 1 over T1. To understand this, let's start with the high temperature regions, higher than the Bison peak. In this temperature region, you have a lot of thermally excited Bison excitations. And such Bison excitations scatter these quasi-localized states and try to delocalize them. As a result, the zero energy peak from the quasi-localized mode gets broadened, and that peak is reduced. However, as decreasing temperature beyond the low energy Bison peak, the Bison density becomes dilute, and the scattering process becomes rare. As a result, this zero energy resonance becomes sharp, then the peak becomes higher. So this picture naturally accounts for this temperature dependence, the flatness at higher temperature, and it shows upturn in the temperature scale of Bison peak. So this is the origin of simultaneous zero mode of around the vacancy, and this picture well accounts for the temperature dependence of 1 over T1. Okay, so finally, let me look a little bit at the specific heat and how fractionalization and impurity effects affect the structure of specific heat. So in the absence of impurity, we have a double peak structure of specific heat. The fermionic excitation accounts for the higher peak, and the Bison excitation accounts for the lower peak. And both these peaks have contribute to the entropy of 1/2 of log 2. So you can find the entropy plateau in between these two peaks. Then what happens if you introduce impurity? This is the impurity contribution to the entropy. So the introduction of impurity reduces the entropy. Then this impurity entropy shows the similar plateau behavior, but the plateau value is not half log 2, but it's a log 2. This can be understood as a convolution of two effects. So firstly, if you remove one spin, so it practically removes one Majorana from the higher peak. Because the removed spin should have fractionalized into two excitations, fermion and Majorana, but that contribution is now missing. So the impurity entropy should be pushed up to half log 2. And another half of log 2 can be understood from the zero mode formation. Because the introduction of impurity inevitably forms the zero energy mode of fermion, so another one fermionic degrees of freedom pushes down to zero temperature. So combining these two effects, we have the entropy plateau of log 2 in this intermediate temperature range. This result is, I think, very important because this high energy peak of specific heat is high energy. It's already observable in a couple of compounds, such as sodium iridate or ruthenium trichloride. But this low energy peak is sometimes masked by the magnetic ordering. But this result shows that even from the high temperature feature, you can capture some evidence, evidence of fractionalization. So the systematic study of introducing impurity and measurement of some entropy, you can identify some features of fractionalization. Okay, so it's almost 35 minutes, but let me summarize my talk. Okay, in this work, we have constructed a new exact analytical solution of dynamical correlation function of Kitaev model. And by using it, we fully explored the dynamical properties of this model with and without impurity. And as a result, we found the zero energy resonance appearing in the vicinity of site vacancy. This site vacant zero mode comes from the simultaneous zero mode of Wison and fermion. And in particular, as to the zero mode of Wison, it originates from the two important properties of Wison. It's always pair created, and it gives pi phase shift to fermion. These two important features of Wisons lead to this zero energy formation. So observing this phenomena, you can catch one essential point of fractional excitation inherent in this Kitaev spin liquid. Okay, this is the end of my talk. Thank you very much for listening.
So the temperature of the Wison peak and the temperature of the fermionic peak, what determines their ratio?
Ratio? Yeah, it's about 10 in this model. But you are asking the energy, what determines the energy scale? It's an important question. So both are proportional to J, right? But the mechanism is very different. So the fermionic peak, it comes from the bandwidth of fermionic excitation. But this Wison peak is kind of, this comes from the scattering process. So it also reflects the detailed band structure of this system. So in this system, we have Dirac points at lower energy. But suppose you have some variants of Kitaev model which have a Fermi surface. Then you have a higher scattering dimension. Then we can expect this Wison energy is pushed to higher energy. So this is a bit difficult, but this is a scattering originated energy scale.
Another point is that if you can calculate for NMR spectrum, if you can calculate a histogram of the local field, at the site, then as a function of impurity, doping or something, then it would be possible to compare with an experiment.
Yeah, of course, yes. Yeah, practically, this plot is something like this. At each temperature, this gives the histogram, yeah.
So I just want to make sure that I understood what you said. So if I introduce vacancies in the honeycomb lattice, the entropy of the higher peak will reduce and move to lower temperatures.
Yes. Yeah.
That will be a signature of fractionalization.
Yes. Yeah.
Thank you.
Any other questions? Yes.
Thanks. So just a question. So so in the pure Kitaev model, which is in the pathological limit, some property may not be extended to the limit where you introduce other generic interactions. Yeah. I'm wondering how many of things are robust against.
As far as the zero energy mode is concerned, it's isolated, so it's some Wison energy gives the protection. So at least perturbatively, that physics is protected. That's my answer. And as to the, for example, static magnetic correlation, it's not that robust because, extremely short-range spin correlation results from the conservation of Wison. If Wison propagates, it acquires a long-range correlation. So in that sense, the static physics gets some correction. That's my answer.
Thanks.
Any other questions? Well, if not, let's thank the speaker once again.